All right, good evening, students. As you can recall, we were on the topic of vectors from last class, and we actually gone through how to work with vector. We know that vector is a quantity that has both magnitude and direction. So when we talk about a quantity, we're talking about something that is measurable, and things around us. In mathematics, we realize that most of what we're doing is really measuring stuff, right? And we have quantities such as length, time, kilogram, grams, temperature. All of those are different quantities that can be measured. So anything that can be measured, we are thinking of that as a quantity. But different quantities will have different what we call unit of measurement. When we're measuring anything to do with mass, we measure it in grams or kilograms, or the submultiples of grams. When we are measuring anything in length, we measure it in meter or any submultiple of meter, like centimeters, decimeter, millimeter. Those are submultiples of the meter. If we are measuring anything in terms of, say, time, we would generally use the smallest unit of measurement, which is seconds, or we may use hours and so on. So quantities are different measurable things that can be measured. Good evening, Ms. Wilson. Right. I must apologize to you all for yesterday. I know I planned to have today's class yesterday, but I was caught up with some things and I could not really get to attend the class. So just please bear with me. So today is our final class. And as I was mentioned, so we started the topic of vectors and we look at what vectors are. So as I was explaining that we have different quantities that require different units of measurement. So we talk about mass in terms of gram or kilogram, length in terms of meters or centimeters, time in terms of hours and seconds, and we talk about temperature. So there are many different things that we can measure, right? Even your electricity, you measure it in terms of kilowatt hours and so on. So there are many things around it that can be measured, but everything that you measure requires some unit of measurement. Now, there are some things that we measure that we refer to as vectors. And those things that are vectors, they are referred to as vectors because their direction matters. So it means that vector quantities are quantities that can be measurable in size and direction. Now, we refer to scalar quantities as those quantities where direction is not important, so there is no need to think about direction. If you're thinking about time and temperature, you're not really thinking in terms of direction, you're just thinking in terms of the size of the quantity, in terms of how much hours are, how much, if you're thinking in terms of just length, you can talk about what distance in terms of meters and centimeters and so on. Now, the key difference with vectors and scalar is that one of them has direction and the other one does not have direction. Now, from the last class, we had looked at how to add two or more vectors. First and foremost, we talk about a vector as being some quantity that is usually not you know, vector quantities may be often a quantity that you are unable to see with your naked eyes, such as force. A force is a quantity that you will experience, but you generally don't see, like gravity. You know that gravity is there because when objects are thrown up, something pull them back down, and we call that force gravity. So force would be a vector quantity, and the direction in which the force is acting would matter. Now, another vector quantity would be like velocity, acceleration. Those, the direction matter. So something that you should understand about vectors, if they are moving quantities and they are moving in some direction, and the direction in which they are moving, they are generally moving within that direction in a straight line. That means vector quantities don't generally go around in curves. They generally travel in straight line. And because we cannot really see them, we often use a line segment, a segment of a line, to represent a vector quantity. And know that I said to represent. That means the line itself is actually not the quantity. It's only a representation of the quantity. So if I use a line of, say, 2 centimeters to be 1 Newton, it means that every 2 centimeters of measurement based on that line will tell you the size of how much Newton you have. So if 2 centimeters equal to a Newton, and you have a line of 20 centimeters, then you will have to divide that 20 by 2 and to determine how many Newtons you have, and that will work out to be 10 Newtons. Now, if you are understanding quite clearly the distinction that I'm trying to make between scalar quantities and vector quantity, raise your hands for me, please. Anybody? All right. So today we are going a little bit more in vector. We had started vector. We had looked at result and vectors. A resultant vector would be that single vector that can replace 2 or more vectors, 2 or more component vectors acting in a way in which that we can apply the triangle law, or we can apply the parallel law. Now, for those who were not able to attend the previous class on vector, all I can say is that I will try to post a video between this evening and tomorrow, so you can view it and see the things that we were discussing in that session, all right? Because we really don't have a lot of time to repeat a lot of things at this point. All right, so what we're looking at today, we say that vectors represent as matrices. All right, now that might sound a little far-fetched, but it is not. When we say vectors represented by matrices, remember I mentioned that we use a line to represent a vector. And if we have a line and we're using a graph paper, then what we will do, we'll represent the endpoints of the line using coordinates, which would be the X and Y coordinates. Raise your hand if you all understand what X and Y coordinates is. Let me see the hand that those who understand clearly what we mean by X and Y coordinates. All right. Now, all right, so on a graph, for those who are not quite clear, on a graph, we have 2 axes. We have the X and Y axis, which is 2 number lines that are intersecting at the 0 position. And if it's a number line, you know, you can count along them. So if you have the two lines and they cross where the zero position is, remember number line has on it positive and negatives. So the two of them cross at zero, then we will call zero the origin, meaning the origin of which you are counting from, right? So every counting must start at zero. So on this horizontal number line going across, we generally refer to this as the horizontal axis. And to the right of zero, we put positive numbers. And to the left of zero, we put negative numbers. Now, the vertical number line is also labeled in the similar fashion, but above we put the positive values, and below we put the negative values. Now, when we talk about coordinates, we're really talking about if you draw a line or a curve, these x and y values. Now, along the horizontal, we have the x values. Along the vertical, we have the y values. So above y will be positive, below is the x-axis, y will be negative. And to the right of the horizontal, x will be positive. To the left of zero, x will be negative, and so on. So in terms of coordinates, let's say that we start a line from zero and we move it in some direction, but the line where it ends, so the line ends at a point. Now the point at which the line ends, we can note the x value at that point. And say, let's say the line ends here. The x value, you just come down to meet the x-axis to read off what the x value is. And let's say that this is x value equal to 4. Now, for your coordinates is the number that we actually put in brackets to represent a point. All right, so this is the x value. We write the x value first, and then we go across the vertical axis, read off what the y value is. Here the y value is 2. So this is our coordinate that marks the end point of a line starting from the origin. Now, this coordinates is how we mark points on a graph. So wherever we want to mark a point, we write out what the x value is first, then we write what is the y value. Is that clear to you, Ms. Shamel?
Yes, sir.
All right, good. Now, when we are representing position vectors, let us look at the definition of a position vector. So the line segment which joins the point of the origin, referring to the origin on a graph, where the two number line cross, the horizontal and the vertical number line. One give you the y-axis, which is the vertical, one give you the x-axis. But the two of them intersect at 0. So that's the origin. So we say that the line segment which joins the point of the origin to some other point is called a position vector. So once there is a point coming from the origin and it ends at some other point, right? This line segment from 0, 0, 0 to 4, 2, this is called a position vector. So position vector must start at the origin and they end at some other point on the graph. So a position vector start at 0, 0 and end at 4, 2. You may have another position vector that starts at the origin and it may go to some other direction with some other point, right? So that is also another position vector. Now, so what you should note about position vector is that they start at the origin, and notice the arrow. The arrow is pointing away from the origin, and the origin is x equals 0 and y equals 0. All right, I'll put that in those brackets. Now, this endpoint for this vector over here would be, let's say, y equals 3 and x equals -1. So this endpoint will be -1 for x and the y value, which is 3. All right. So this position vector starts from 0 and ends at -1 and 3. Now, we generally refer to these coordinates as our endpoint for the vectors. But if we should write these coordinates such that the numbers are in a column form, whereas you would write the x coordinate above. So for this one, you would have -1 above and 3 below. That means above would be the x and below would be the y coordinate. So all you're doing, you're just flipping this vertical, right? So these coordinates are horizontal. The numbers are arranged horizontally. But when you're writing them as a position vector, you write them vertically, starting with the x above and the y below. Raise your hand if you are understanding clearly. Now, when you write them vertically, you don't really need to put any comma on that in between. Is that clear, guys? Raise your hand. Ms. Chamel, are you good with what I'm explaining?
Sir, I understand.
Okay. Ms. Wilson, are you good with that?
Yes, sir.
Ms. Cabrera?
Yes, sir.
Ms. Green?
Yes, sir.
All right, good. So it's good that everybody is on the same page. So let me clear this now and look at some further definitions. All right, so here now we have the line OP, and this is a position vector of P, right? So it starts at the origin OO and it ends at P. Now, position vectors represent as column matrix. Now, if the coordinates of P, xy, are xy, then the position vector OP in the previous slide above is xy. Now, this previous slide above, what you notice, if you read along the x-axis, so moving along the x-axis, so here we would have 3 going right up to the end point of P. Over here, you'll also have 3 coming right across to the end point of P. So it means that the end point of P coordinates will be 3, 3. And if you're going to write these as a column matrix, 3 above and 3 below, then once you write it in the column matrix form, you're writing your coordinates in a vector form. All right? And so that's what we mean by when we're representing vectors on a graph, we generally write the coordinates in the column matrix. All right, guys, everyone is good with that. All right, so here we say that so if the coordinates of P are xy, then the position vector of OP in the previous slide would be XY. Now, the point P is 3, 3. So the position vector of OP is 3, 3. Now, one thing that we know about vectors, we must know the magnitude. The magnitude of a vector is actually the length of the line segment that is representing the vector. So this is a vector. And if you want to find the magnitude of this vector, meaning the length of this line, or in the sense of it's a part of a line, so let's say the length of this line segment, then what you would do if you're trying to find the length of this line, now you will realize that you should be able to apply Pythagoras' theorem. Now, if you're applying Pythagoras' theorem to finding the length of a line, what it really means for a position vector, you're really going to try to find the length by constructing this line into a right angle triangle by drawing a vertical line from the end point and then draw a horizontal line from the O to where these 2 points meet, and then clearly have a right angle triangle. Now, one of the things that we would know that the coordinates here would be 3. That means the x value, the x length, this length here would be x equals 3. That's the entire length from here to here. So x is equal to 3. And if you're going upward, we see that y would be also equal to 3. So it means that the y, in terms of the triangle, this vertical line would be the length in the y direction. So we would have that length to be 3. Now, if you want to find the length of OP, which is the magnitude of that line, or the size of that line, then we can apply Pythagoras' theorem. Because anybody recall what Pythagoras' theorem states?
A squared plus b squared equals c squared.
All right, so in terms of this diagram, and we want to find the length of OP, how would we actually write it in terms of Pythagoras' theorem? What side of the triangle we're trying to find? We're trying to find OP. So OP would be what side of the triangle in terms of
Hypotenuse, sir.
all right, so OP is the hypotenuse. And when we're starting Pythagoras' theorem, the formula starts with the hypotenuse as the subject. So we are going to have OB squared is equal to the opposite. And this would, if you're considering this angle down here, this side would be opposite. So it would be 3 squared plus the side adjacent, so plus 3 squared. Right. Now, of course, you would actually find the square root of the squares when you sum them. So you work out what is under the square root sign. So you would say 3 squared, 3 3s, 9, plus 9. Then you sum them. Then OP would actually be the square root of 9 plus 9, which would be 18. And that's how you actually work out the magnitude of a position vector. So you use the the coordinates at the endpoint at the vector to give it the x length and the y length. So the first coordinate is the x coordinate, and the second coordinate is the y coordinate. So in terms of a formula then, you're really using Pythagoras' theorem. All right. So here, when we look at the magnitude now, the magnitude is sometimes called the modulus, which is the same thing as the magnitude, really referring to the length of the line or the line segment that you're using to represent the vector. And so we can write this formula, the square root of x squared plus y squared. So that will give you the magnitude of a position vector. So you put in the x value and the y value. All right, any question about that, guys? Raise your hand if you're with me and you're understanding clearly. Any question that you want to ask before we move along? So for vector quantities, your main calculation is to find the magnitude, which is the length of the vector. And if you know the coordinates of the vector, then you use this formula to find the magnitude. But remember now, you have not described the vector completely by just stating the magnitude alone. You also need to state the direction. Give me a second, guys. Sorry about that, guys. So everybody is good with how to find the magnitude by using the coordinates of the vector. Remember, if you have the vector in the column form, the x coordinate is the one above and the y coordinate is the one below in the column matrix. So if you are finding the magnitude, you would use these two values in the column in terms of this formula, which is actually Pythagoras' theorem. All right, so as I was saying, it is not complete to only state the magnitude of a vector. Because remember, a vector has a magnitude as well as a direction. So if you only calculate the magnitude and give that as your answer, you are really not completely describing the vector, because if you have magnitude only, it means that you're dealing with a scalar quantity, and scalar quantities only have magnitude, but vector quantities must have magnitude and direction. So if you calculate the magnitude, then you also need to calculate the direction. Now, how do we calculate the direction of a position vector? Now, we would have learned some things from trigonometry that will help us in terms of finding the direction. But before we move on to the direction, let's talk a little bit about negative of a vector. Now, we would have looked at this from the previous class. It is the same idea, same concept. So the only difference now is that we were referring to the vectors without a graph paper. But now that we're referring to it with a graph paper, it means that we can represent the vectors based on their coordinates. All right, so if we have a vector, and let's say that its coordinates written in column form or column matrix would be 5, 2. Now, the negative of this vector simply would mean that you would find the negative values of their coordinates. So going from, if you're moving in direction from the point A to B, and these are your coordinates, positive 5 for the X and negative and positive 2 for the Y, it means that if you're going from A to B, you would have positive 5 and positive 2. But if we are now going in the reverse direction from B to A, then it means that you're going in the opposite direction. And for vectors, the moment you are going in opposite direction, then the vector, the coordinates has to be negative, right? So for negative vectors, you use the opposite direction, which is indicated by a negative sign. So once you put a negative sign on the values of a vector, you are saying that the direction now is going in the opposite. All right, guys? So if this vector here going from A to B, then this vector down here is going from B to A. And notice that in terms of vector notation, this is how we show the direction. The arrow above helps to show the direction because the tail of this arrow starts at this letter A and it ends at the letter B. Now, if you're going in the opposite direction, that means the tail going to start at B and it going to end at A, right? So whereas this vector AB is positive, the vector AB is positive 5 for the X and positive 2 for the Y. The vector BA going opposite. So now you have negative 5, so negative 45 and negative 42. And notice for the vector notation, the letters are reversed. So instead of starting off with A, you're now starting off with B, and the arrow tail is at B, and it ends at A. Raise your hand, guys, if what I'm explaining is clear to you in terms of the concept. All right, good. Miss Shamel, I told me that she might be in and out. Miss Shamel, are you there?
Yes, sir, I'm here.
Okay. Are you following the concept so far?
Yes, sir.
Okay. All right. Now, for vectors on a graph,